Thanks, Jeff, and thank you for convert my PowerPoint slide into PDF. Yesterday, I was in the Econometrics conference at the Quality University in Sydney. And I was the only one use PowerPoint slides in the room. My name is Dong Sun from James Cook University, and the topic is trade liberalization, export, product innovation. Arguably, innovation plays a very important role in profitability and growth. And researchers have been broadly innovation and export different dimensions, theoretically and empirically. Most of these studies explore international trade and innovation of forms other than product innovation. But product innovations means firms produce new product. The definition of new product follows pretty much follows the OECD definition. Important point is that it's new to the firms, not necessarily new to the industry. Indeed, new to the firms. So we're going to look at firms' decision on export and product innovation, both theoretically and empirically. Basically, we're going to look at there's a trade liberalization shock. How does it affect export, product innovation, transmit industry? So we're going to model theoretically. We're going to model firms' behavior in the multi-stage framework. Firms make decisions on entry, whether to innovate, career product innovation, and setting prices in both the domestic market and foreign market, which are monopolistic competitive. So we're going to feature a mixed static dynamic. Then we utilize China's WTO shock during WTO in 2003. How this affects firms' export and how, in fact, it's transmitted into firms' optimal decision to innovate. So the identification strategy. So basically, what I'm going to do is impose a theoretical model over the data, utilize structural relationship implies in the modeling for identifications. For example, utilize the variation in the sample, like increase in the marginal due to the trade liberalization shock. There's an increase in the marginal benefit patients. Then firms that never innovate, it will take time to innovate because they need to set up lab, hire people. Firms that already innovate previously, it'll be easier for them to start. So there exists variation of response by this new type of firm, which for the source of identification. The story is essentially I can summarize one sentence. Basically, what I'm going to tell you, hopefully in a convincing way, is that okay, joining WTO reduce the iceberg trading cost, and now like give firms incentive immediately because marginal benefit innovate now is higher than marginal benefit if for exporting firms than now. So that's a static incentive for firms. Then as firms start to innovate, they predict that they're going to move to a better productivity state in the future. So that's one dynamic benefit. In addition, if they start innovations, then the next year they can save some cost, the entry cost of the innovation. So that's a second dynamic benefit. So the study is related to existing literature on export and innovations of this. So let me just introduce our analytical framework. So in each period, the entry firms will draw two capability called capability endowment. Number one, number two. Number one is for production. Number two is for innovations. Higher value means more doing both sense. And now they're going to consider whether they want to enter the market or not. If they decided not to enter the market, then they are not observed. Yeah. Now this is sample selection. Okay, if they decided to enter the market, then now there's shock happen, something happen. Okay, and then firms maybe then firms need to think whether should they leave the market. If they say okay, they are going to leave the market, now they are not observing the data, and that's sample attrition, and it's also endogenous. If they decided to stay in the market, then now they consider they should innovate or exit. And this is plenty of photo. So if they decided to okay, if they decided that yes, okay, then they will decide optimal level of product innovation, and then set price for domestic foreign market. If yes, no, release, so forth. Okay. So these two-level decisions is static. Basically, firms will make choice. Great, margin benefit. That's always. Decision on innovation, the X is that because now the decision today will affect them. And also exit entry. So it's mixed static framework. I do not have any specific attack. Because right, information. Firms have perfect information in the current period, including shocks at stage 2. However, their information on the future is imperfect, so they need to form belief. The equilibrium is the set of optimal decisions on exit, entry, exit, whether to innovate, export, optimal level of product innovation, and the process in the domestic foreign market, together with the cut-off capability, that create a market, and the firms believe are correct. So basically, we are going to use firms believe are correct that have in order to do an estimation. Here's the model. Q is the quantity demand. A is aggregate demand. Income demand, price index. P is the price. Rho is the split one. Is parameter. So the Q, the output is a CS aggregation of all products, all existing product, and QN is a new product, new to the firm. And it's CS aggregated. We are going to choose numeraire property, so that the aggregation parameter is otherwise it's not identical. And data is measures the relative attractiveness of the new product against it's the marginal ratio new and old. And similar, there's a one for to tilde is for foreign market, the same motion. Technology. Firms and the production, firms need to pay a fixed cost production. Then combines 1 unit labor with M unit material. Produce S unit. It's S, it's S depends on 2 factors. The firm's endowment, lambda 1, so higher lambda, and also another side that is observed. Then if firm decided to produce new product, there's an additional fixed cost of innovation. Then combining 1 unit labor with M unit media input, produce lambda 2S new product. So lambda 2 is that it firms capability of innovation. Higher lambda 2, higher, more capable identity. And then given this production technology, we work out the marginal cost. Marginal cost. So here, eta here is the ratio of new product against the old product. And this is the endogenous from choose eta. Great. Firms per period profit from domestic market. E minus marginal cost and quantity. So take away the fixed cost production and the fixed cost of innovation. Chi1 is equal to 1 if firm started to zero. So the cost of innovation is there are two components. One is FN, which is a fixed cost of innovation. The other is the FNE, entry cost. This entry cost, firms can save if a firm's already enrolled previous one negative one. So that is the innovation of to export, firms need to, there's also a fixed cost of export, entry cost, FEN. And there's also iceberg of trade cost. And we can write out the export profit as the equation here. Then solve the model back. By the way, mention, okay, entry firm play this part. If it's a firm's incumbent firm, only play. Sorry. There's the next period. So this is one period. But anyway, this is not a game. Yes, they are. So when a firm decided to innovate next year, this day. Oh, okay. So this degree of innovation, optimal level of innovation, the eta is static, but whether to innovate is dynamic. So if a firm decided to innovate, then choose the optimal level of innovation. So solve the problem. Price, just optimal price markup on top of the margin. Markup depends on the profits. Yeah, CEO vision. Then firm's optimal level of product innovation. Should they decide to innovate? It depends on two factors. First, how capable firm are. The more capable firm are, the more innovation is going to do. Theta is how attractive the new product are. Then we can write up the profit. The profit, if decided Taiwan equal to 0, that's the optimal profit. If Taiwan equal to 1, it's this. If firms export without product innovation, that's a profit. Export with product innovation, that's profit. We're going to observe that so if there's an increase in tau, the marginal benefit for, okay, compare this. This is the export profit of innovation without innovation. If there's a decrease in tau, which is the iceberg trading cost, then marginal benefit. So that give you firms a static incentive. If firms decided, okay, because of trade cost decrease, firms want to export, then they have bigger incentive. Okay, let's static one. Okay, at stage 3, if a firm decides to innovate for export. So the entry cost would be 12. One of the export previous year. And in addition, decision at stage 3, the fact that the evolution of the state variable. So psi, which is the observed component of the firm, and W is the wage rate, total wage divided by number of workers, M is the intermediate. So in making decisions, firms form belief on the evolution of state variables. So basically, for the future shocks, firms understand that there's a probability that it's going to be very rainy day. I'm going to leave the market. Okay. Conditional, I'm going to stay on market. I forecast the future aggregate demand by this period. So into some sort of category. Then for the firm's individual state variables, we're going to, this is continuous variable. It's like it follows a discrete state markup chain, conditional on entry and stay in the market, where the transition probability will depend on its decision on whether to innovate. And the firms will, maybe I shouldn't say estimate, I should say predict. Okay, predict the transition probability from the data or whatever information is available. And this is an equivalent form of prediction that allow us to estimate. So given firms belief, then we can write out the value function. For example, the value of Chi1 Chi2 equals 0, no innovation. So Chi1 is innovation, Chi2 is then we are going to normalize by fixed cost function. That's why if the reason is relative to measure the relative. So that this is per period flow payoff plus a continuation value. So stage 2, if the realized shock is very bad, then it just firms just exit. Stage 1, if then firms does not show favorable capability endowment, it does not enter. And this all right, so how do we do the estimation? The step 1, we are going to first estimate yes, or and true. So firms profit maximization, charging a markup on top of margin cost. Price total variable cost function. There's a relationship, structural relationship, total variable cost. Germany, So in the estimation, we are going to focus first on the non-exporting firms, so estimate the growth, and then using exporting firms, estimate the growth. Step 2, we estimate the impact of trade liberalization, China's WTO accession, from the iceberg. Again, now we have a structural relationship, optimal revenue and optimal export revenue. Okay, so we can work out. We have this. This is tau. This is the iceberg trade. Now we have raw material data. Observe the revenue, export revenue, income at least so and this is the price index. So given this structural relationship, then we can formulate this equation. So the impact of WTO accession is identified in different way, not different. So it's before, after, and after change of aspect trading cost. Now, in order to estimate the dynamic decisions on whether to innovate the export, we need to have probability of condition probability by state value. So we create relative six. I mean, how many points? Sample, how many data appear in this year? No, next year. Okay, so for the state variable, we have data for W plus M, which plus the linear input, and for the psi is observed component activity. We assume it depends on one side. We know the total number of workers and fixed asset component. Then we utilize principal component. And then square out into four categories. We should think this is as kind of a approximation. The key the trade-off that the next year there's only small number from small proportion of. It's even more small proportion of. So at the end, if I have many, say, continuous, many categories, then when I estimate the probability, the frequency, I get a 0, 1, and I don't know whether 0 goes up. I don't have data. Really, that's why I choose that only. For the decisions on whether to innovate export, dynamic discrete choice modeling. And I wanted to acknowledge here, 3 years ago, 2022, I attended this workshop, same workshop at ANU. And I recognized quite a few familiar faces in the audience. So the inputs are very much appreciated, like Victor, like Bob, like Patel, and also Peter, all these are, and John Ross. These methods, I applied what I learned. So those I did a kind of brief visualization. First, this whole term 1 over F. F is export production. A is the average demand. Lambda 1 is the production capabilities or something, which the whole term is draw from log normal. Similar for this, and for this term R constant term, fixed fact of holding over fixed cost of production is parameter at least. Okay, so on and so forth. Then the new value choice function is so at this step, the known parameters and the value functions is now I already have raw CS parameter in hand. I estimate the exit probability. I estimate the transition probability matrix now. This we set discount rate to 5%. That's standard. I do not intend to leave that. Then we draw from this distribution and condition on this. We can come. Okay, condition on this with the case of beta. I need that. Okay. These betas, they are primarily I want to estimate. So condition. So with the case of beta, then we can work out with the draw of this case of beta, we can work out the value function. So and here there's this. Oh, basically this is what. All right. Thank you. And then we can simulate really. And here I wanted to, to point out that here we are restricting the case where this is positive. Basically, this is where we can address the sample cycle. And we know that my interest is Taiwan, Taiwan, whether to innovate and whether to X. So these are both dummy variable. So the modification is also dummy variable. And we have this mathematical identity. You take an expectation, you get a probability. So another list, a natural estimator, it's better to minimize the sum of square error. This one. So beta hat. Data, so pretty much standard data, okay. So many people are using this set of data. It's a little bit old now. But I focus on the air conditioning. And this, I'm going to jump a little bit, sorry about this. This is a summary statistic. These are kind of reduced form results. Basically, it says that positive correlation with innovation. If you X five, the preference parameter, raw domestic one is 0.75, foreign market is 0.91. So that implies that the foreign market is has higher elasticity of substitution, which seems makes sense. This is the effect of WTO station. So basically, that's 13%, 13.5% after WTO as well. If we allow for 1 year lag, let's if we using year dummy, okay, then we find that it's probably we do not have other factors. So the estimate 2003, we don't have data. 2005, 2006, okay, here's another benefit. I show you this. So this is transition metric. If no export, no innovation, then if I'm at state 1, I have roughly 0.29 increase, move to state 2, 3. In contrast, if I export and innovate, I start with state 1, I have 50% of moving up. Okay, so this we observe this first order stochastic dominance. Okay, I did not take. So basically, it says that if I innovate, I export, I can predict a high performance going up. Better. So that's kind of thing. And here you see that when I focus on Taiwan, I got some zero. And it's not clear whether it's zero is because it's really zero. I do later on in the partnership who used to, okay. So this is last slide. Taking up. So basically, the point here is that beta 3, beta 5 measures the entry cost. It's a lot higher than the fixed cost. So this pattern is kind of consistent. That's 1% type of. They look at only export. Let me just summarize. Basically, my story is that given it's traded validation, export loses that incentive from innovate. There's a marginal benefit bigger for exporting from China. And then as firms starting to innovate, at high probability of moving up, better scale, and also can save the entry cost. Okay. And that's all I want to share. Thank you.
Hello, everyone. I'm Chunnan Xu, a third-year PhD student in the Department of Finance at Southern University of Science and Technology. It's my honor to present the collaborative work of our team, which includes Dr. Xin Huang and my supervisor, Professor Zhao Junyang. The title of our talk is Dynamic Incentives for Screening and Monitoring in Venture Capital. Let me briefly outline what I'll cover today. First, I'll introduce motivation and main contributions. Then I provide a detailed introduction to the base model, which considers screening only. Then I'll briefly introduce the extended model, which incorporates screening and monitoring. Finally, I'll provide some practical implications of our model. It is well known that VC plays a role in selecting and nurturing high potential startups. VCs performs two critical activities. The first is screening, means selecting high quality projects ex ante, and this is a one-shot effort. And the second is monitoring, means managing projects post-investment, and this is ongoing efforts. Both efforts are costly and unobservable to outside investors. So without proper incentives, VCs may screen carelessly and monitoring poorly, leading to project failures and investor losses. The question is, how do we design optimal incentive mechanisms for these very two different types of effort? And this is what our research addresses. Before presenting our contributions, let me clarify the research gap. Existing continuous time models, particularly Sannikov's 2008 seminal work, focus on ongoing monitoring efforts. These are actions taken repeatedly over time with transient effects on project output. But screening is fundamentally different. It is a one-shot action taken at inception, but has persistent effects on the project output. Recently, Grigorowitz et al. 2024 addresses screening for bank loans, where uncertainty is driven by default risk, which is characterized by an exponentially distributed random variable. Our contribution is to model screen for high-risk venture capital projects, where uncertainty follows Brownian motion, and this requires fundamentally different method. So here comes our first contribution. We developed a novel methodology combining generalized Lagrangian multipliers with Mayer transformation techniques. And this is the first continuous time model designed specifically for screening high-risk investment projects. We found that for the screening-only model, the optimal contract involves a lump sum payment when output hits a time-dependent threshold. And this threshold is linear plus exponential growth in time. And especially when principal and agent are equally patient, the first best optimality is achieved. We also extended our model to incorporate both monitoring and screening, and we found that the optimal contract is VC keeps a fraction of equity and receive dividends when his promised value exceeds a time-varying threshold. And finally, our model provides theoretic foundations for the widely used hurdle rates in practice. Now, let me clarify the screening-only model. We consider the classical principal-agent framework. The principal, which I'll call P, is a risk-neutral investor with discount rate R and deep pockets. And the agent, which I'll call A, is a risk-neutral manager with discount rate gamma. We assume that gamma is bigger than R, which means A is more impatient than P. Captures is borrowing constraints or higher opportunity cost. Also, we also assume that A has limited liability, which means the payment to ACT must be non-negative. And also, A's outside option value is assumed to be constant R. The project output evolves according to the stochastic differential equation, which is given by equation 1. Here, mu is a project's intrinsic potential, which is determined by A's one-shot action at time 0. Better screening means higher mu, and the cost of screening is assumed to be quadratic. The key friction here is mu is hidden. P cannot observe A's action, but XT is observable to both parties. Sigma is volatility representing project risk, which is exogenous, and ZT is a Brownian motion. The key feature here is that the screening effort is one shot but affects output forever. Yes, there's no adverse selection. Yeah, here is the screening means selecting high quality projects from a pooling of candidates. But adverse selection means design contracts, less informed parties design contracts to involves to incentive type the specific actions. So this is different. Here's the timeline. First, he offers a contract specifying payment to A, C, and the termination time of the project tau. If A accepts this contract, he chooses his screening effort mu, and then A can pursue his outside option R. Then finally, the project runs, and A receives payments according to the payment. Note that everything happens at time 0 except the project's operation itself. So tau it's a termination time of the contract. After that, the contract ends and the project A ends. Yeah. So P's problem is to maximize her expected profits, which is the present value of output minus payments to A by choosing the contract C tau and the recommended effort mu. She faces 3 constraints. The first is incentive compatibility, which means the recommended effort mu star must be optimal for A given this contract. And the second is participation constraint, which means its value from this contract must exceed his outside option R. And third is limited liability, means the payments to A must be non-negative. So let's first consider the benchmark model where all decisions are contractable, and we can easily derive that the optimal recommended effort mu FD equals 1 over psi R, and this is a benchmark. Then we solve the second best case, namely our moral hazard problem, where its screening effort is not contractable. So in this case, if P paid A as what she does in the first best situation, then the best choice of way A with hidden screening is doing nothing. That is mu equals 0. Therefore, P must postpone the payment to incentivize A. Recall that A's problem is to solve this maximization problem. And the key challenge here is that CT is independent on XT, thus dependent on mu, but in an unknown form. Thus, we cannot solve this problem by the first order condition. Our solution is to use manual transformation techniques. The idea is elegant. Instead of saying mu change drift of XT, we say mu change probability distribution of X. That is, under P, XT evolves with no drift, while under manual P mu, XT evolves with drift mu. The random nicotine derivative between P mu and P is given by gamma T, which captures how mu affects the probability weighting. This manual transformation allows us to separate optimization over mu from optimization over the contract. So A's problem can be reformulated as the equation 3. We note that the expectation E mu and E are taken under P mu and P respectively. So under measure P mu, CT is dependent on mu, but under measure P, the influence of mu on CT is encapsulated in the random nicotine derivative gamma T. Thus, we can solve this problem by the first order condition and get the agent incentive compatibility, which is given by equation 4. Thus, we can also reformulate this problem under the probability P mu. And this is a maximization with constraints, and we solve it use the Lagrangian method. That is, P needs to solve the equation 5. And note that the coefficient of DCT shown in the blue part, as we assume that DCT is non-negative. So we prove that the payment happens when the coefficient of DCT is 0. So here's our main result. Suppose A is more impatient, then the optimal contract has a simple structure. That is, his payment to A is made at most once in a non-sum M tau star. And the payment occurs at a stopping time tau star, which is the first time the standard Brownian motion ZT mu hits a threshold. And the intuition is fascinating since A is more impatient, so P wants to pay early. But to provide incentive, screening incentive, he must wait for a signal that mu is high. And this trade-off is reflected by the exponential growth of the with T. And it grows larger as the discount rate spread gamma minus R is larger. Or equivalently, we can say the payment happens when the performance xt hits a time-dependent curve. And thus, this optimal contract is characterized by these parameters, which satisfies the system of equations involving FOC, IC, and PC. An important refinement is that we can implement the contract by a constant payment M, independent of the payment time. And we prove that this just works as well and is simpler to implement. So P's problem reduced to 3 objectives. The first is a constant C and eta that define the payment threshold, and the constant M long-sum payment, while the third is a recommended effort mu. So we also solve this problem by Lagrangian method. But notice here, the problem involves the expectation of exponential discounting evaluated at a stopping tau star. As far as we know, when gamma is bigger than R, the threshold grows exponentially. There's no explicit solution to this expectation. So we can only solve it, compute it by numerical method. But when gamma equals R, the threshold becomes constant. Thus, this expectation has an explicit solution. So we can derive everything explicitly of this contract. That is the payment threshold Z bar star, the long-sum payment M star, and the optimal effort mu star. Note that the mu star is the same as the first best case, which means when P and A are equally patient, the optimal contract achieves first best optimality. The moral hazard is completely eliminated. So why does this happen? That is because when gamma equals R, there is no incentive cost from delaying payment. So P can set an actually high threshold to perfectly infer Mu's screening effort. The key result is zero incentive cost, thus achieving the 100% contract efficiency. But if gamma is bigger than R, there is deadlock risk from delayed payment. The first best is untenable. Then here's the solution for the case where gamma is bigger than R. Since the expectation of this exponential discounting has no explicit solution, so we compute it by Monte Carlo method. And this figure shows how the equilibrium changes with the promised value W. We can say high promised value leads to lower effort mu. This moral hazard modification is consistent with empirical evidence that study has found piece rate workers are more productive than fixed wage workers. The intuition is because where sale agents has less incentive to work hard. And this figure shows the effect of the project risk sigma. We can say that higher risk leads to higher payment threshold, that is increasing C. And this means P must set a higher bar to provide the same incentive. Why? Because in a noisy environment, PA can more easily hide his low effort from behind the randomness. So to prevent this free riding, P must demand a stronger performance before paying. Yes, because we computed the expectation by Monte Carlo method, so there is some computation error. So the curve is not so smooth. And this figure shows the effect of the screening difficulty measured by the screening cost coefficient psi. We can say higher screening difficulty leads to lower screening equilibrium effort mu and higher payment threshold. So the reduction in mu is straightforward, but the rise in the payment threshold occurs because lower effort mu leads to a lower value of the claim, just analogous to a perpetual knocking option. And this figure shows the effect of the ACE discount rate gamma. We can say more impatient agent get paid earlier, but provide lower effort, since the discount rate spread drives the incentive cost. So the larger gamma minus R, the more costly it is to provide the screening incentive from the delay in payment. Okay, now let me briefly introduce the extended model, which incorporates the monitoring effort, that is AT, and we assume it is the cost is linear, measured by the coefficient theta. So this creates a double moral hazard. We must incentive both screening and monitoring. For monitoring, A must bear continuous risk, so his promised value must be sensitive to the performance. And for screening, A needs to skin in the game from the start. Here's the result. We can say that this has a richer structure. So if gamma is bigger than R, then in the optimal contract, A maintains a promised value account WT. The WT is his distinct value of his future payment. The payment paid if and only if WT exceeds a time varying threshold WT1, which is endogenously determined by our model. And in fact, it's determined by a system of partial partial differential equations. So detailed techniques can be seen in our paper. And the projects terminate if WT means his previous value count hits his outside option R. And the monitoring effort is achieved at a constant level, which is A bar. And with this sensitivity coefficient beta T, that is the sensitivity of his promised value to the output performance XC. So this contract resembles an equity with dividend cap. We can say compare with the screen-only case where a single non-sum payment is considered. Adding monitoring changes the structure of the contract dramatically from a knock-in option to a equity stake continual payment scheme. Finally, I'll explain interesting implications of our model. So it is common in VC, PE, and hedge funds that agent receives incentive fees only after returns exceed a threshold. So our model provides a theoretical foundation for this. That is, this threshold provide screening incentive. But the most importantly is that we gives the optimal hurdle rate endogenously based on the project risk sigma and the screening cost psi. Empirically, the hurdle rate ranges from 6 to 2% in practice, and our model shows that this should vary with the project characteristics rather than a fixed level. But our model gets the constant threshold when gamma equals R, that is P and A are equally patient, which also provides a justification for the practice used constant hurdle rate. And so this finding maybe can provide some empirical justification in the future. Okay, let me summarize our work briefly. We use a novel method to model the one-shot screening incentives in continuous style. And we found that for the screen-only model, optimal contract is like a perpetual knock-in option. And this threshold is endogenous determined, which is linear plus exponential growth in time. And when P and A are equally patient, the contract achieves first best optimality. And we also extend the model to both screening and monitoring. And in this case, we found the optimal contract resembles equity-like, that the payment is paid only when his promised value exceeds a time varying threshold, which is also endogenously determined by our model. Thanks for your attention. I'm happy to take questions. Yeah. Project portfolio. Yeah. Okay, maybe that's a question that can be discussed in future study, because here we focus on the risk projects, means the VC keeps selecting the projects are also very risky, and they want to get higher payment, so not consider the portfolio product.
Okay, so Alex Chow, I'm doing PhD in Korean UBC. So this is a joint work with Professor Hiro Kasahara, who is my supervisor, and also with Professor Yuichi Sugita. So I was recently added as a co-author, so the latest job with my name will be available very, very soon. So yeah, so production function. So production function is widely used in the literature. So naturally speaking, by definition, one should observe the variation in both output and input to identify production function. But unfortunately, with most of the firm level data sets, they only contains revenue data, but not the output quantity data. So like to bypass this, many studies in the literature just use revenue divided by a common industry price index as a proxy for output, which unless under some very special circumstances like perfect competition, it would generally lead to bias in markup, TFP, or other model the concerning model objects. So it motivates a research gap that can we still identify production function, TFP markups, and consumer demand system from the firm revenue data without the output quantity data. So this paper answer this question that not only we could identify a production function, TFP, markup of quantity, but also we could identify a class of monopolistic competition demand system, which is the HSA demand system, with the corresponding consumer utility function, such that we could do the counterfactual welfare analysis of the market outcomes or market power. And this paper, we also developed a semi-parametric estimator, which works well as evidenced by Monte Carlo simulation. And we apply our estimator to Chilean manufacturing plant with a standard data to conduct the welfare analysis for firm's market power. So let's talk about the setup here. So the lowercase letters are all in log scale. Okay, so we start with the inverse demand curve. So price depends on output Y and demand shock epsilon. So for the sake of identification, we will transform the epsilon demand shock or normalize it to be a quantile of epsilon, which is U, or the rank of epsilon by the CDF, such that the demand shock is temporary in a way that's independent to the information set 2 periods ago. And then we have a revenue here. So revenue is just price plus output. And then we define this function as sine function in terms of Y and U. And then we have our markups with P over MC by the definition. So okay, we have output Y equals to the production function F plus TFP omega, where X are the input variables like capital, labor, and material. And we also assume that the TFP follows the first order Markov stationary process such that the innovation shock ID, which is ether. So we're doing an identification under the short run perspective. So like the only flexible variable input variable here is the material, and then we assume that the capital and labor follows some stochastic process that depends on the past information set. And then we make some standard assumption in literature that there's an independence of the innovation shock to the past variables. Also, we make assumption of the innovation shock that is independent to the normalized demand shock. Okay, so firm observe omega K L U to do profit maximization. So from the FOC, there would be an equilibrium demand function M here. And as standard in the literature, we assume there's monotonicity between omega and M such that there exists an M inverse function. And then we can write down a model of TFP process and revenue functions in terms of their structure M inverse, psi, F, H, which are to be identified. And so, okay, identification here. So I only have 3 minutes, so like simple setting. So there's a parametric setting to illustrate the essence of our non-parametric identification argument. So we start with the AR1 TFP process, and then we use Cobb-Douglas production function. And with the Cobb-Douglas production function, we could actually have the separability of the M inverse function such that it depends on a non-parametric function lambda, depends only on M and U, and linear in K and L. So like this already is very useful to simplify the things. So there exists a fine function in terms of M and U that equals to the revenue. And we also assume there's a MA1 demand shock, so like justify a temporary demand shock assumption. And so under some mild conditions, there will be a monotonicity between the revenue and the normalized demand shock U. And then we can do the inversion here. And it's pretty natural to do, so U is a normalized demand shock, so it's like a quantile. So it's pretty natural to use quantile regression. But the issue here is like there's an endogeneity problem such that because firms first observe the demand shock and then they make decisions on M. So these are clearly an endogeneity problem. So which is a structural selection mechanism. So we should like use our assumption of the temporary demand shock such that we could do IVQR in a way that the exogenous variation of the M T minus 2 it's generating exogenous variation in M by the M T minus 2 to do the identification of U IT here, normalized demand shock, and the phi t function. So intuitively, why we want to do this step first, because we need to have a U, because when I identify the control function, there's in terms of the U. Okay, so the next thing here is, yes. Yes, and then the main reason is U itself is naturally a quantile of epsilon. So like we could like trace a quantile, and then if we have some like IV here with this like the temporary demand shock, we could do the IV version of QR. This is a CDF. So like this is a quantile of the epsilon. So this is CDF. So, okay, so next is the control function. So to do that, we should make some like normalization assumption. So this normalization assumption here is same as doing scale and location normalization, which means that we could only identify the M inverse up to scale and location from the conditional CDF, where the V here is independent to the innovation shock. So what does it mean? It means that we could only identify like A plus B times M inverse, where we actually don't know what's A and B. Okay. But this is not the weakness of our identification strategy, but rather this is more like a structural limitation that is the best we could identify. So to see this, we can like look at these two restrictions here. That's okay, we try to identify M inverse here. But if we multiply the both equation to both sides, constant B, then BM inverse is actually it's possible to satisfy this two restriction by having a BM inverse T minus 1, B times ether, B times lambda, B times theta K, B times theta L. And the same is go for a locations thing. So like there's a structural limitation that we can only identify this M inverse up to scan location. Okay. So this is a normalization business, which is pretty usual in the projection function literature. And so yeah. So for the algorithm strategy we're doing here, we want to make some linkage between like M and ether. So for the ether here, we just use these two restrictions to write down this ether, which is a blue object, and then we'll set this aside, and then we'll come back to this later. But the more important thing is like the ether. If we use the AR1 TFP process, okay, to write ether in this way, and because of there's a monotonicity between M and omega, if we're conditioning on the phi, the red objects here, then it's as if saying that there would be a monotonicity between M and ether. Okay. So it means that the quantile of M given V will be the same as the quantile of ether given V. Okay. So this is the conditional CDF. The G is the conditional CDF. And then if we use the second assumption here, we can get rid of the conditional set. And then if you put our blue ingredient in the previous slide, then we will get the ether in a useful representation to do the identification. So what's the key? The key is just differentiate and define. Okay, so we observe the conditional CDF. Okay, and what we are doing here is just like differentiating with respect to k and kt minus 1, such that the derivatives are also observable. And then we take the ratio, and then we could identify the rho here. And then, so this is the idea that could be used to do some other things. So if we do the same thing to m with respect to m with respect to k, then like we will have our first equation here. The red objects are the things we want to identify. And then with the scale and location normalization, scale and location normalization here, we can have the so it's 1 minus 0 in the first line. And then with the Cobb-Douglas separability here, we will have the difference of lambda function evaluated at different m1 star and m0 star. And by the fundamental theorem of calculus, we can write this as an integral of the derivatives, such that this derivatives, the derivative in the third line here, is basically the blue object above, which is observable, evaluated at u star in the conditioning set phi. So like if we keep putting like substitution in the equation, then theta k is like identify up to scale, because if we move the st to the left-hand side, it's 1 over st. So basically we could scale the theta k up and down because like because of the st, because the st here depends on normalization constant we are picking, the m0 star, m1 star, and u star. Okay. So we're saying this under upscale because like we don't know what's the scale of theta k. It could be up and down, scaling up and down. But let's say it's under scale. Then we put this theta k back to the first equation. Then we identify d lambda dm up to same scale. And then we can also identify the same thing like by doing the same differentiation and define, because we identified the k already, and they're all identified up to same scale. And then with the partial derivatives of lambda, with the m and with respect to u, by integration, we can identify lambda function at up to scale and location. So then we have a lambda, we have theta k and theta l. We could identify the control function up to the same scale and same location using this Cobb-Douglas separability here. And then like this is like, so basically this model has two unobserved heterogeneities. The first one is the like the normalized demand shock. The second one is the TFP, which is the control function. And then we've identified like both of them already. So now it's just basically, if we solve the unobserved heterogeneity, what remains is just, using the identity of the revenue function and also using the FOC or the locus formula, where the material share, the red object in the second equation, is observed. That's two equations, two unknown, to solve for a d sine by dy, which is 1 over markup by definition, and the theta m up to the same scale before. And then, so thetas are up to the scale. And then the m inverse is up to scale and location. So the outputs here is up to scale and location. So far, these objects are just like, some of these objects just identify up to scale and location. And the next question is like, how can we solve for this, like recover the scale and location with some like economic meaning or more reasonably with some like assumptions? So like here is, so let's clarify what we actually identify. So we actually identify theta tilde, okay? And then if we want to link the theta tilde back to the primitive, the primitive actual thetas, we could link it back by a scale constant b, right? Because theta is either up to scale. And then like using the second equation, if we are willing to assume a return to scale, which is let's say constant return to scale c equals 1, then we can solve for b. And if we can solve for b, then like we could identify what's for the theta m, theta f under this constant return to scale normalization. And then the same thing's happening to m inverse, because we identify the m inverse tilde, which is up to scale and location. If we have assumed the TFP follow the AR1 process, so zero mean, okay. Take the expectation, then we can actually identify what is the location constant of the m tilde inverse. So it means that we could identify the output fully because we solve for the scale, solve for the location, and then we can identify the revenue function from R, Y, and U by just non-parametric regression. So all the constraint model objects are fully identified with this normalization. So this is our first contribution, that how could we identify the model structures with revenue data correctly? Okay. But the next question is like, if we have these identified objects, how can we use these objects to do some counterfactual analysis? Okay. So we want to do some counterfactual welfare analysis in market power. So we should like define a homothetic singular gradient HSA demand system by Mastriyama and Yushev. So this is characterized by revenue equals to S star, which is the primitive budget or market share, plus the log of total income, or the log of total industry revenue phi here, where the Q here is the aggregate quantity index. So this is a class of a demand system that is extension of the CS demand with CS and SS linear and Y, and this allow like a state dependent substitution patterns. The HSA demand system is more flexible and also allow our incomplete pass through for sure. So yeah, so this is our demand system we want to do. So the quick for here is like, can we just do the counterfactual without like think about this like demand system just with the objects that we just identified? And the answer is no, because the identified reduced form here, the psi function here, is actually not invariant to the change in aggregate state due to the change in quantity index. So if we shift the states, let's say we shift the whole state to perfect competition, then we will have a totally different aggregate states, vector of output and vector of like demand shock. Then the Q here is actually hidden in this red object reduced form here in this psi function. So if we don't have this primitive function identified, basically based on the psi function we just identified, we do not know what is the another psi function in another state. Okay. So we need to do something to identify the S star for the counterfactual analysis. And then, so this is a assumption that, okay, multiplicity competition, no free entry, and take the Q and phi as given. And then we normalize the baseline aggregate state as Q equals 0. Then we have the proposition that, okay, we could actually, based on what we have identified, we can actually identify the primitive budget share function. And there exists a unique and homothetic preference that generates this system such that the utility function is identified for doing some welfare analysis in terms of compensating variation. Yes. So if we have homothetic preference, this share function is independent of phi. And then this is very important in a way that, so this demand system is like the Q here is alone is a sufficient statistics to characterize this demand system. So if we have a different, if we have a non-homothetic preference such that the phi is entering here, then given these assumptions here, we could not identify the S star. Unlike maybe you can normalize the phi entering this like budget share function, but the issue is like, when we think about counterfactual, unlike this normalization here, which is pretty harmless to do counterfactual because we care about a change in the quantity index when we transfer to another state, normalizing an income level is very harmful to do counterfactual analysis, because like if you pick different normalization of the income level for a normal homothetic preference, you will have a totally different counterfactual welfare outcome. Okay, yeah. So okay, so we have the budget share. We have the answers identified. Let's do some counterfactual. We do shift our multiplicity competition to the marginal cross pricing equilibrium, which is perfect competition with markups equal to 1. Okay, we make an assumption that firm at just only M, so a short run thing, while keeping K, L, U, omega the same, and the income fixed across both states as well. So so here is like we want to via a set of like output quantity Y and Q that solve this M+1 equation. So for each firm, MR equals MC for multiplicity competition, right? And subject to this sum of share equals to 1 constraint. So we have n plus 1 equation for this n plus 1 variables. And based on the assumption we make, the Q here should be 0 if we solve it. Because the S star is identified as the baseline in the baseline state that Q is 0. Okay. So we solve for the multiplicity competition equilibrium with what we identify. Then we do the same to the marginal cost price equilibrium, the perfect competition, such that it's just P equals MC. Okay, the market is in 1. And then we solve for the same thing. And we can have we can then have the aggregate output vector such that we want to find what is the compensating variation such that the utility across both states is the same. So phi plus CV here is the income. Okay, we want to see how much income should the consumer, the representative consumer change to reach the same utility. And also we could also have the short-run profit change, which is just our accounting identity in some way. And so this is the original argument, and then let's talk about estimation. So basically, we follow pretty similar steps as the adaptation arguments. So IVQR, so GMM quantile regression recurrence smoothing. Second step, probability estimation, and then at the end we do some use all the identities to recover all the and FOC to recover all the other objects here. But the interesting part here is there is a parametric HSA demand system that we're considering in a way that is our hat here is the demand system. So this is interesting in the sense that if beta is converging to 0, this R hat is converging to a CES demand system. So it gives some testable implication that where the HSA, whether we could reject the CES and in favor of the HSA. So simulation is HSA demand, couplerless, L1 TFP, M1 demand shock, same thing. So we want to also compare our method with the ACF method, which is our commonly used method in the literature, apply with reference as output to see the bias. So this is a theta M, the material elasticity. And we can see the blue lines here, the true values. So our method cluster around the true value, while the ACF1 is biased. Same for capital, same for the labor. So we have also the demand system parameters to show that we cover the demand systems pretty well. We also want to see the estimated versus the true TFP and markup. So they're aligned around the 45 degrees line. So yeah, they estimated pretty well. Okay, so applied it there. So 3 largest industry, 31, 32, 38. Excluded firms. So this is a standard sample filtering rule anyway. And then we also have the non-parametric bootstrap to get the standard error. And so it doesn't take too long for each industry. So the first thing here is, so this is a Poisson function estimation, the average markup, which is pretty reasonable and comparable to the literature. So the next thing is we see an interesting implication is okay, if beta is converging to 0, then it's a CS demand system. And then we have the standard error here. So these are NRS style of estimation with generated generative variables, right? Or GMM, generative variables. So we could, if the standard error is correct, then we could do the usual t-test. And then the standard error is much less than the estimate. So we conclude that we could reject the CS demand system in favor of our HSA demand system. So this is the alignment. So R hat is the estimated demand system. R is the observed reference area. So it shows that it fits pretty well for 31, 32. And 48 is a bit worse because the sample size is lower, and for industry phase or is yeah, there's something happening there. And so this is more interesting. So we have 4 steps, right? So the first step is based on the non-parametric, or like we do not impose any parametric demand system in the first step to recover the normalized demand shock. And then in the 4th step, we impose our parametric excessive demand system. So we want to see like how well a parametric demand system is going to like align with our non-parametric estimate of the rank or quantity of the demand shock. So as you can see here, they work pretty well. One thing here is because in the NRS we are doing, we also we also penalize the difference between the first step estimate and the 4th step estimate. This gives the composite NRS. But yeah, they look pretty well. Okay, so the last thing is about welfare cost. So if we solve all those like n+1 equations and do all the things, then we can see that so in terms of the percentage of industry revenue, the overall welfare loss. So the CV is on the consumer side. The PMI price is on its firm profit side. So the overall welfare is around 3 to 6% if we shift from the perfect competition to the monopolistic competition. So this paper, provide the allocation of production function, TFP, and markup, as well as the HS demand system. So we found a way to identify the HS demand system to enable the counterfactual analysis correctly, which could not be done with the reference production function as in the literature. We need to have a proper identification argument to do the reference data to do all this counterfactual analysis properly. And we have a good estimator, and then we applied to the manufacturing plan data, and then we can reject the CS demand. And the counterfactual analysis show that the market power reduced for welfare by 3 to 6% of industrial revenue. So yes, I think this is my presentation. The first part is like, so before step 4, everything could be done purely non-parametrically. So none of the demand system is imposed before the HSA demand system. Before step 4. So like back to here, if we go back to here, we only need to assume monopolistic competition to have all this demand curve nicely like well behaved. But that's what we need. Yeah. The key restriction I would say is follow the so it's more like we don't assume the common pricing at the first place, and then we follow all the step that's like there would generate a different markup or take account into those like demand curve properly. So we do not need actually demand, but like what we are saying is like at the beginning, the revenue function and the demand curve itself looks totally differently than like perfect competition style thing. So we take account into those things and then run all the identification arguments step by step to bypass the issue or like to like not to do the identification step by step properly. So this is more like step-by-step argument to realize that if we make the assumption that we are in a multiplicity competition, yes, then this is how we should do to do the identification, but not just by assuming that every firms take the price as given. Yeah. Yes. True, yeah. So for the demand shock demand shock independent to like the ether, so they're temporary in the sense that because when we are doing a control function identification here, we need that to get rid of this conditional set to for identification. So so the whole identification, okay, so so if we impose the HSA demand system, probably we may have some sort of like over-identifying restriction to test whether like this serially dependent or not, or like MA1, AR1. But still, like if we follow the allocation step by step, we need to have that independence at the very beginning to identify the TFP. And then all the remaining objects are recovered based on this assumption. So maybe one way to do it could be we impose the demand system at the very beginning. And then maybe there's a way to like parametrically could test something like that. So we not just actual rank, but actual demand shock. But like in this agriculture argument, we need to follow this step by step. But that's a very good point. And then we will think about like how to like proceed in this way. Yeah. But this is a very important point about this demand shock too. Yeah. Yes. So in GNR, I think they use the first order conditions, the cost sharing. So like we took that as a way uh, I remember the paper also like make some other assumptions that are not very they try to like if I remember they try to do constant elastic demand thing, if I remember correctly, on those like revenue data thing. But like this is non-parametric argument. But for this presentation, this is like Cobb Douglas, as you like everything's parametric. But on the paper, everything's non-parametric. So we could have that kind of, elevation beyond the GNL contribution in this sense. You mean the Cobb Douglas? All right. With the CES demand function, it works too. It will work too, but this is a more flexible class of the demand system we're encountering. So this HSA allows for like state dependent. So in CES, like the quantity index is just a linear in Y, but in HSA it could be a state dependent substitution, and it allows incomplete pass through. So with CS it works because this HSA demand system nests to the CS, so we could test it. And so it's more like what kind of parametric assumption we're imposing to do the identification. But here it's just showing a nutshell of like, okay, under these parametric assumptions, and this is the essence of the non-parametric argument, but like we could have a fully non-parametric identification argument. But for the estimator, actually we kind of tried to make it more non-parametric, but like it doesn't work very, very well because as you can see, this 4-step estimator, there are issues with that. So, but yeah, but thanks for comment. Yeah, it's very